Okay, so I will introduce the topics of quantum metrology and its applications, and some classes of strategies involved in quantum metrology with their strict hierarchies. So this presentation is based mainly on the paper, The Optimal Strategies of Quantum Metrology with a Strict Hierarchy, published on a Physics Review Letter by Professor Yuxiang Yang from the University of Hong Kong. So I'll first introduce the framework of quantum metrology. A typical measurement of a physical quantity will involve preparing a probe and let it interact with the environment that is encoded with a physical parameter, and then do the readout on the probe. So quantum metrology have an analogous framework. It prepares a probe, and with some auxiliary bits like the ancillars on the quantum circuit, and apply some correlations on them, something like the entanglement, including like the Hadamard gate or the control knot bits to change the joint state of the probe and the ancillars, and let it interact with the environment that is encoded with our targeted physical parameter. We denote it as a variant of phi, and actually we can denote it as a unitary operator, that is the E sub phi, and then we apply the correlation again. Sometimes we actually will have the inverse, operations, that is of the primitive one, and then I do some measurements to read out. And the workflow, so the workflow typically includes the probe state preparations and state interaction of the system, and the parameter readout through the state measurement, often described as a series of quantum measurements. That is usual practice. And to describe the quantum metrology scenarios, so an instance of metrology strategy can be modeled as a tuple, and the tuple, the rho describe the density operator of the prepared probe state, and E sub phi, this is the quantum channel encoded with the some information on phi in a certain manner. Actually, we always build up some prior models, prior relations of the E sub phi and phi. N specifies the number of identical unknown channels available. So channels typically is a quantum operations, that quantum operations that is analogous to E sub phi, and a graph structure G specifies the network of experiment circuit. So for each node in this graph, this is one of the quantum resource, or the quantum channels, or I apply the measurement at that certain point. So these are all the possibilities we have for the graph structure. And the asymptotic behavior of the metrology readout, the error of the metrology with respect to n is sometimes of our interest. And a majority of the work of quantum metrology is based on the analysis of such asymptotic behavior. Although actually there are some non-asymptotic behavior, they focus on the concentrations of the metrology readout with respect to the ground truth in a concentration manner. So that goes maybe that goes the field of high dimensional statistics. So here are some instances of quantum metrology scenarios. So they're identified by CC, CQ, QC, QQ. Here are 4 typical ones and also a sequential ones. These are the figures from the quantum metrology. This is a paper. This is a review that is really classical in this field, and almost every paper published, it will cite this article because it includes the basic framework. Yeah, they often cite some refer to some content in this paper when they are doing the introduction. And CQ stands for separable state and general measurement. So, and CC is separable state and measurements. So it's simply parallel. We simply repeat the parallel experiment for like n times, and this will reduce to a classical system. And the classical system, in the classical system, the asymptotic behavior of the readout errors will like governed by the central limit theorem. That is a classical one. And as for CQ, QC, and QQ, we introduce the entanglement, and that will bring in some potential enhancement of the metrology performance. And the sequential ones. The sequential one means that like in this picture, the quantum channel is no longer be arranged in a parallel manner. Actually, after the quantum state interact with one of the quantum channels, it will like being applied to another correlation operator, and then applied to another identical quantum channels, and just so far, and in an analogous way, and do the remaining ones. So until it uses up all the n available quantum channels, and then finally do the readout. And we will investigate this, how this will bring some enhancement to the eventual performance compared to the parallel ones in the later context. Okay, so what are the applications of quantum metrology? Since we have introduced the framework, and you might ask, what's the application of this? So this is a way to realize more flexible and accurate measurement. So sometimes the measurement, they are really vulnerable to external noise, and quantum metrology brings in a potential solution for this problem, because sometimes in the macro metrology pictures, the interaction of macro particle to the system actually will destroy the physical quantity that we want to measure. So with low asymptotic behavior on the error, quantum metrology will be a potential solution to this problem. And to specify, so with a basic n-cubic probe that is entangled, it can enhance the error from O n minus 1/2 to the O(n) times capital N minus 1/2 with n repeated experiments. So this is a direct result from the central limit theorems. So this is the enhancement on the standard deviation. But for this, with the quantum entanglement, it will bring an n minus 1/2 enhancement. And also, the way that for the second advantage, the way that parameters are organized can be changed. So originally, if we want to measure theta, so quantum metrology will enable the measure of f theta. And sometimes if theta is encoded with like the normal noise sigma k, so we can improve it into this one. So improve from f v plus sigma k to the noise is encoded to the total readout. This will potentially avoid the accumulation of errors in the measurement system, and this will actually bring a large enhancement to the performance. This will be a potential direction for future research, actually. And I saw in a recent conference paper that they actually utilized this property to enhance the performance of measurement errors. And okay, so now we begin to investigate how to optimize quantum metrology scenarios. So this is a model of quantum metrology and how this will build up the model that we want to investigate. So in a nutshell, optimal strategy aims to utilize limit number of queries to the black box quantum channel. Yes, the quantum channel encoded with our unknown parameter phi, such that we can acquire as much information about it as possible. So this is a picture. We have probes. We have a collection of probes, and we take out one of them, kept phi to the black box common channel, and after E phi is interacted with this quantum state, it goes back to the collection of quantum probes for future use. And every time we want to take out one of the quantum states and let it interact with the black box, and we will see after after using n of the black box quantum channels, and how much we can get about the uncertainty about the our prediction on the quantum on the physical parameter. So we start to formalize the optimization objective and figure out what we are actually optimizing. So we are using the uncertainty sigma phi hat of the estimator, phi hat, we establish from interaction of the black box common channel to evaluate the amount of information we have on phi. So we are switching from introducing the general framework to examine the specific values we are investigating. So an auxiliary theorem can help to transform this can help to establish the performance metric. So we are introducing the quantum Cramer-Rao bound. It says that within a multi-iterative experiment, our uncertainty about the parameter can be lower bounded by this 1 over square root of mu j sub q rho phi. So rho phi, jq is the quantum Fisher information, and for each operator that is encoded with the physical parameter, physical quantity phi, this is the minimum of the inner product of partial phi with respect to this capital phi, capital psi phi, such that with an extra ancilla A that corresponds to the Hilbert space H sub A, tracing out the partial, taking the partial trace with respect to the system with ensemble cat phi will result in our primitive density operator. So in this formulation, we called cat psi phi as a purification of rho phi with an extra ancilla A. So it tends to minimize the inner product, the norm of this factor partial phi psi sub phi square. And this is taking the partial derivative with respect to the unknown parameter phi by treating this psi phi as a function, as a mapping of phi. And this is the quantum Fisher information, and we know that this is lower bounded by this one. So we can see that if we split it into two parts, mu this and jq, square root of this, and this is what the central limit theorem can guarantee. And if what we want to do is let this jq as large as possible. Actually, in the theorem, it is proved that the quantum Cramer-Rao bound is attainable. It can be saturated by designing a specific scenario for single parameter estimation. It is attainable. But for the multi-parameter estimation, it is remain unknown that whether under what conditions the QCRB can be saturated. But at least for the single one, we know that this is for sure. So we want to let this as large as possible. And actually, we are doing a max-min. Max is like rho phi, and min is taking the internal optimization problem. So how to depict a strategy in extracting the information? This is of usual practice that we define the Choi isomorphism of an operator, that is the quantum channel encoded with the information we are interested in. We denoted by E sub phi by noticing that we are using the capital E instead of the calligraphy E. So the definition of Choi isomorphism is as follows. And this is so each parameterized operator can be regarded as a linear map to the set in this set. It's mapping the linear map on the Hilbert space H sub 2i minus 1 to the H sub 2i. And this is the linear space of linear mappings. This is a linear the space of linear maps from the space of linear map to a space of linear maps. So H sub 2i minus 1 and H sub 2i are the input-output space of a single query. It means that we are having a calligraphy E sub v, and the input space where suppose this is the ith query to the unknown quantum channel encoded with v, and we denote the input space as H sub 2i minus 1 and output space as H sub 2i, and both are Hilbert spaces. And this is raising from like E is tensoring with identical maps, and times these are the operators of the same structure as the leading ones. So the strategy can be regarded as arrangement of physical processes, like what we have discussed in the last slide. So consider that we are having F as a future space, or I would say the eventual output space of our queries. So a total strategy can be characterized by a Choi operator on the space of linear maps on this space, and this tensors of the leading H sub I spaces is the spaces of n queries, and the H sub f is the future space, that is where the output of n queries will live in. The quantum state of the eventual output from the n queries will live in this space. Intuitively, if you want to we want to regard a strategy as a concatenation of two sub-strategies, as what we are doing in like the Bellman equations and dynamic programming. And also, we can use a Choi operator of two corresponds to the two sub-strategies, and we denote them by A and B. And their underlying Hilbert spaces are indexed by calligraphy A and calligraphy B respectively. So we define their concatenation by the link product. So the total strategy represented by the two strategy operators A and B is denoted by the A star B. That is, we are taking the identity maps on the B set minus A tensors the operator A taking the transpose with respect to the Hilbert spaces corresponding to index set A's cap B, and times the B taking the tensor product of the identity maps on the Hilbert space corresponds to the index set calligraphy A set minus calligraphy B, and we trace out the space where they're intersecting. Yes, so A and B, they have underlying Hilbert spaces. Tensors index belongs to calligraphy A, and we are tensoring it. And this belongs to the definition. And we analogously define the strategy set. So we have already defined how the concatenation of two strategy will behave as a joint process, and we analogously define the strategy set denoted by P by any subset of the following universal set of strategy. The strategy is any operator P belongs to the space of linear maps on this joint space where each operator P is semi positive definite, and each rank of P equals to 1. So the rank constraint is raised because we want to ensure the utilization of pure process. So we are not considering like a mixed process, a mixture of strategies, like what we are having in the game theory, that we are having the lambda transpose P such that lambda transpose 1 equals to 1. And this is a convex combination of the operators and the strategies in the strategy set. And we are not considering it. It is of usual practice that if we are like mixing two strategies, that is mixing two strategies that have more than one strategies, it will yield a total rank that is higher than 1. So we are restricting it to be exactly 1. And suppose we treat the n queries to an n tensor of Choi operator that is like this, and E sub phi is defined in the previous sections, and concatenate with our proposed strategy set P. And this will result in a complete process, P star and sub phi. So actually this is like we are having like the P is our strategy we can control and concatenate it with our queries. So actually some of the part of the queries can go intermediately into our strategy. And actually they are in a mixed manner instead of like really in a sequential manner. So the QFI of the output quantum state from above process, it is defined as the following. So this is defined to be the our optimal strategy in the strategy set P of this joint process. We are taking the supremum of this. If we this is the quantum Fisher information induced by P and N sub phi. We attempt to reformulate above definition in a more controllable manner, because actually in under the last scenarios we are introducing a more complicated maximization problem, and actually the inner one will induce a minimization problem. So we are having a max min problem. So we try to reformulate it into a more controllable form, that we can actually see what which variable we can control. So if P is a subset of strategy set, so since it has rank 1, it can be decomposed into a form of cat p bra p, where cat p is a quantum state in this space. So we consider ultraspectral decomposition of n sub phi that so it will have this spectrum, and we denote it as n sub phi dagger, where n sub phi is by concatenating all the eigenstate. So we're taking the R as the maximal rank with respect to n sub phi squared. So an operator that is similar to this. So actually this decomposition is non-unique. This is up to a unitary operator. It can, so for an operator n sub phi tilde that is similar to n sub phi, so n tilde sub phi and tilde phi dagger will also be the composition of the primitive n sub phi. So actually we are having n sub phi tilde equals to n sub phi v sub phi for an arbitrary unitary operator. So if we set the omega sub phi equals to this one, and we notice that P link product and sub phi will be in this form, and we claim that this is a purification of this by some calculations. I have done the calculation in a slide, but I will not. This is some basic linear algebra, and we will find that this is exactly the purification of this. Oh, sorry, it should not be tilde. This is the primitive operator n sub phi. By noticing that this is n phi and phi dagger. Yes. Yes. Oh, yes. This is exactly the form. And so by the objective of minimization in QFI, we see that if we are taking partial derivative of phi of this purification, it will yield the following form. And we denote this, we have already denoted as 1/4 sigma phi, omega phi, and there will be this one. So times 4 times the objective, 4 times the quantum efficient information, it will yield raise P. So in the paper, the freedom of choice, they will goes to the unitary operator V sub phi. So they reformulate the form of primitive QFI as sub JQ P link product and sub phi as supremum minimum of trace of P and 1/f, identity operator 1f tensors omega sub phi. So by noticing that if we take a partial derivative with this one, actually partial derivative of n sub phi v sub phi, it will give this n sub phi partial phi v phi. So partial phi v phi partial phi v phi n phi will equals to minus n phi n partial phi v phi. And by reformulating, taking h as this one, it will result in this expressions. So mathematical simplicity, we also consider a strategy set P tilde as the by tracing out the subsystem F for any P in the strategy set P. So together with the min-max theorem, actually we can we originally have sub-min. Actually, after exchanging, we have min sub. And also by the fact that this set is compact. So the sub will be exchanged into max. And we result in this min-max form such that P tilde belongs to this set, the convex hole formed by an affine space of Hermitian operators. And it is required to be positive, semi-definite. And we are taking the union of all this such sets. So this handling the form of P tilde like this is just for simplicity. So in that paper, they only investigated a form like that. So the QFI will be the optimal value of the following constraint optimization problem, and by formulating this is a theorem, and let's have a sketch proof sketch of this one. And due to the loose correlation between H and P, we can see that for the first and the second stage of optimization, actually the variable H and P tilde, they're actually not that correlated. So we can start by fixing H and solve the internal maximization problem, and then we optimize with respect to H on the optimal solution. So we choose a affine basis for S, for overline S, and this is actually the dual space. This is the dual space of S sub I, and we can reformulate the internal maximization problem as this one. So the dual space requires that transpose of SIQIJ equals to 1, since QIJ is a affine basis of this affine dual space. And the condition by dropping the QI greater or equals to 1, we formulate the dual problem by calculating Lagrangian, and we can see that it results in this form. It's quite simple and require that the multiplier x sub I as an operator form to be positive semi-definite. And the only possible case is that all the internal coefficients will become 0. This is a usual practice by in formulating the Lagrangian, and it will give us xi equals to summing lambda ij qij minus sigma sub phi edge that is positive semi-definite, and lambda equals to summing ij, lambda ij is, they are also equals. And by combining these two conditions, we have, by setting the q sub I equals to this form, we'll actually have q sub I also belongs to the dual affine space, because each q sub ij belongs to the space. So we have the dual problem being the minimization over lambda qi lambda, such that this operator is greater than this. Actually, lambda qi greater or equals to sigma phi h. This is equivalent to lambda q sub I minus omega phi h. There's positive semi-definite. And actually, we are safe to combine them, because for the external one, we are minimizing h. For the internal one, we are minimizing lambda qi. We successfully exchange the max to the min, and this reformulation will not bring any optimality gap, because the reduced problem is consistent with the primitive one. So we take each lambda q sub I to be 1 plus epsilon times the sigma phi h, the norm of the sigma phi h, times identity map for some epsilon that's slightly larger than 0. We will have this one will lies in the feasibility region, will yield a non-empty interior because this constraint is non-active. So since the relative interior is non-empty, so by the slightest condition, the strong duality holds. So we are safe to reformulate. We do the reformulation. So the one natural question might be raised is that actually by reformulating the problem, we are changing the optimization variable y tilde p into the q sub I, h, and lambda. So the primitive variable p is hidden. So how do we recover the optimal strategy p once we have obtained the optimal values? The paper proposed an algorithm to recover the strategy p from the optimal value. So by the property of fxy, where the min-max theorem holds. So if we denote x sub 0, y1, x sub 1, y sub 0 to solve the min-max and max-min problem respectively, we will have that x sub 0, y sub 0 is a saddle of fxy. So they solve these two questions respectively. So it means that once we have obtained one dimension of the solution, we can substitute into another problem and solve for another dimension of the the solution. So we have x sub 0, we can recover y sub 0. So analogously, so if the edge of the optimal edge is returned as the optimal solution, and to find the corresponding p optimal y tilde p, we can find y tilde p such that this equals to 0. And in the paper, they skip the calculation and claim that it suffices to find the optimal y tilde p such that the real part of this function equals to 0. So the corresponding scenario can be recovered by finding the optimal p such that tracing out the system on F will result in the y tilde p we found. So after formulating the problem statement, the optimization objective, and the methodologies, they tested 5 different families of strategies. And for the first one, the parallel, the second one, sequential, and the third one is switch, and fourth and fifth one, they're quite general. There's casual superposition order and general indefinite casual order. So I will skip all the detailed forms of the sequences of strategies at each level because they're quite tedious. You can see that defining the switch strategy is quite tedious because it requires some peer-to-peer permutation, and actually is permutation. And actually, for n queries, they can actually be n factorial permutations of it, and actually the computation complexity can be really high. But fortunately, they succeeded in formulating like the symmetry reduced optimization, and by finding some symmetry relations, they reduce the dimension of the constraint from like the thousands, from the scale of millions into the scale of 10,000s. And in the paper, they investigated the case when n only equals to 2. The process encoding will be the first utilize the spinning, the time spinning operations on the z-axis, and then apply the two Corral's damping channels. You can see that damping coefficient is 1 over square root of 1 minus p on the excited state, and the square root of p on the coupling operator. So after evaluating the performance, they found that the QFI under different scenarios, they actually have a hierarchy. So for 984 outcomes from the 1,000 random samples of noise channels, a strict hierarchy was found. With respect to the damping coefficient P, they found that the QFI of parallel is strictly less than sequential, is strictly less than the superposition, and strictly less than the final one, the general indefinite casual order. So it implied a powerful potential of casual superposition strategy among all the cases. And as we can see that the larger the QFI, the more certain we are on the estimation of hat phi on the unknown parameter. So they are the first one to propose an algorithm based on semi-definite programming to formulate all these quantum identities, and they did found a strict hierarchy. So maybe the future research directions will be among how we can fully utilize the ICO strategy under complicated cases. As you can see that for this case, this is quite straightforward, and the scale of the problem is quite small. but maybe in the future ones, they will analyze the more complicated, and they can prove that under what conditions this strict hierarchy will hold. And yes, actually they will be quite hard, but believe that the talented researchers, they will actually find a way out eventually. Okay, so thank you. And this is the presentation I want to make on the topic of quantum metrology.